All right. Hi, everyone. My name is Moaz. I'm a GIS analyst with BC Timber Sales, and I'm based in Nelson in the Kootenay region. My background is in geomatics for environmental monitoring and natural resource management, and I've been with the government for almost 2 years. Today I'm going to share with you a tool I developed for mapping the snow cover extent from multispectral satellite imagery. I call it the Snow Explorer tool. Um, so the main purpose of the tool is to provide our field staff with a quick way to check whether an operating area or specific location is accessible and snow-free, and that helps them better schedule their spring field activities, mostly silviculture stuff like tree planting, brushing, and surveys. The snow mapping approach implemented in this tool is based on Sentinel-2 imagery. In the coming slides, I will give more information on Sentinel-2 and the processing happening in the back end of the tool. The tool is published as a web application. It's developed using Google Earth Engine, which is a cloud-based platform for processing geospatial data. I will not cover details about Earth Engine today. It's a great tool. I think it deserves its own presentation, and I'm pretty sure it will be covered in the coming webinars. So the imagery used for snow detection is from the Sentinel-2 mission, which is composed of two identical multispectral satellites operated by the European Space Agency. Sentinel-2 is part of an Earth observation program called Copernicus. There is currently 7 other Sentinel satellites already in orbit under this program, both radar and multispectral, and a few other missions are scheduled for launch in the coming years. The missions, I mean the Copernicus missions, cover a wide range of applications, mostly for land, ocean, and atmospheric monitoring. So combined, these two Sentinel-2 satellites provide an image of the same location every 5 days. For comparison, Landsat revisit frequency is 16 days. So this is a great advantage if you need more frequent acquisitions for your project. The table on the right has the technical specifications of Sentinel-2. I mean the Sentinel-2 bands. The spatial resolution ranges from 10 to 60 meters. Basically, the visible and near-infrared bands have a 10-meter resolution. The shortwave infrared and red band are 20 meters, and the rest are at 60 meters. Also notice that most bands are covering the red and near-infrared parts of the spectrum, and that's because Sentinel-2 is focalized on land and vegetation monitoring. Sentinel-2 is provided in 2 processing levels. Level 1C is corrected at top of atmosphere, and starting from late 2018, a surface reflectance product was made available, so you can use the imagery directly without having to perform any kind of calibration or correction. This is super important if you're doing time series analysis or need to compare objects through different images or sensors. So the snow mapping technique used in the tool is mainly based on the normalized difference snow index, or simply NDSI, which is one of the most used indices to detect snow from multispectral measurements. As you can see on this spectral profile, snow typically has a high reflectance in the visible portion of the spectrum, especially in the green part, and a very low reflectance in the shortwave infrared. So this characteristic is used to detect snow from imagery by calculating the ratio of green and shortwave infrared bands. And that's where this NDSI formula is coming from. NDSI is a normalized index, as the formula shows. It ranges from -1 to 1 with values higher than 0.3 usually mean the presence of snow in the pixel. The very low reflectance of snow in the shortwave infrared is also useful for distinguishing snow from clouds. If you look at the left side image, which has only the visible bands, it's almost impossible to differentiate snow from the clouds, simply because they both reflect very highly in the visible portion of the spectrum. But as the snow reflectance drops significantly in the shortwave infrared, clouds magically appear as we introduce the sphere bands, and it becomes easier to distinguish between the two classes, as you can see on the right side image. So what I'm trying to say here is that snow is extracted by applying a high NDSI threshold value to the image, and that also allows a good separation of clouds, or most clouds, and snow. The processing workflow I implemented on the tool is inspired from this European research, the TS Snow Collection. It's a great publication. If you're working on operational snow mapping, you should definitely check this one out. So as I mentioned in the beginning, the processing is done in Earth Engine. So the tool doesn't download or process any images on the local drive. Everything is done on the cloud. And my version of the workflow is adapted for Earth Engine logic. So the first step of the process is to search the Sentinel-2 catalog for images based on the dates and the region of interest entered by the user. Images with more than 30% clouds are then filtered out, and the rest are sorted chronologically. So this prepares the images for the next step, in which the tool creates a mosaic of the most recent images available with minimum clouds. Note that the mosaicing step is only performed if the ROI is covering multiple Sentinel-2 tiles. Otherwise, a single image is used. And the final step is to apply the conditions used to classify each pixel to either snow, cloud, or no snow. These conditions are based on pixel-wise thresholds of Sentinel-2 bands. The ones used here are the cloud probability, the near infrared, and the red band. In addition, of course, to the NDSI calculated as part of the process. Notice here that a red band threshold, band 4 in this case, is used along with the NDSI to detect snow. And the reason is that turbid water surfaces like some lakes and rivers may also have a high NDSI value and can be mistaken for snow. But since water has a low reflectance and the red band, it can be used to further distinguish between snow and water. It's demonstrated here in these examples. In the first classification, this one in the middle, only an NDSI threshold is used. As you can see, the river here is misclassified as snow. The misclassification is fixed here on the second image as we add the red band threshold. And the river is no longer classified as snow. So that was all for the backend processing. Let's take a look now at the user interface. I will quickly demonstrate how the tool works. I got it open here. So this is the web application. It's hosted on the Google Cloud, and it's publicly accessible, so anyone can use it. Just make sure to run it either on Chrome or Firefox. It doesn't work on Internet Explorer like any other Earth Engine application. The user interface is really simple and straightforward. The user needs to enter the two search parameters, the date range and the region of interest. The start and end dates are set by default to the last 30 days, but you can modify them by using the same date format. There is no run button. Once the user draws an ROI on the map, the tool will automatically run and perform all the backend processing I explained earlier. I will run an example here. Here, for example, it takes few seconds to generate the outputs. So if all goes well, we have 3 layers. The first, we got a digital elevation model. It's derived from SRTM data and resampled to 90 meters. And this layer is added just to help the user estimate the snow line elevation. Then we got the Sentinel-2 image used to extract the snow cover. As I mentioned it earlier, the algorithm is set to select the newest image with less than 30% clouds and create a mosaic if the ROI is covering multiple Sentinel-2 tiles. If the tool can't find any images, a message will be displayed asking the user to modify the date range. And the third layer, the most important one, is the snow cover extent. It has 3 classes, snow, clouds, and no snow. The no snow class is transparent here. The map is, of course, interactive. You can zoom in and out and play with the transparency to better interpret the results. Yeah, that's pretty much it. That's how to use the tool. It's really simple. I will go back now to my slides and talk a bit about the limitations of this tool. Okay, slideshow. So the first limitation to mention is that due to the spatial resolution, Sentinel-2 cannot detect small objects. For example, not all forest roads are visible, only the major ones, as you can see on the comparison with the very high resolution imagery of Google Earth. So the tool is actually intended to provide the general snow cover and help estimate the snow line elevation. The algorithm may also fail to detect snow in very dense forest areas, as the tree canopy can hide snow from the sensor. This usually happens when the canopy is so dense that the satellite cannot see the snow underneath the trees. And of course, we got the clouds. If you're working with optical imagery, clouds are the biggest limitation. In this case, it limits access to recent acquisitions and partially obscure images. This constraint can actually be overcome by using radar imagery, since microwave signals are not impeded by clouds. Snow detection techniques from radar usually use either backscatter or interferometry analysis. I made some tests tried extracting snow from backscatter measurements from Sentinel-1, but I couldn't get good results, mainly because the C-band signal is not sensitive enough to dry snow. It's able to penetrate it, actually. Repeat pass interferometry, on the other hand, can detect snow with reasonable accuracy, according to some studies. But this kind of analysis is not currently supported in Earth Engine, and the processing is much more complicated than optical imagery. But well, that's another story for another day. And that's all I have to share with you. One last thing, actually, just to let you know that the source code of this application is available on GitHub. The main code is in JavaScript. I also included a Python version, but it has only the processing part without the user interface. So yeah, feel free to check it out and contribute to the project if you want. And I'm done now. Let me know if you have any questions.
Oh, that was great. Moaz, there's a few questions in the chat box. Maybe we'll start with those ones.
Okay.
One was, is there an ideal size for like the bounding box that you're using? If you did like all of BC, for instance, would it still work?
Well, yeah, there is actually a kind of a usage quota per application. It's basically there to prevent users from submitting massive computation requests and overload the server. So yeah, you can actually run pretty big areas, but I usually run it for few our operating areas, which are maybe 50 square kilometers or something.
Yeah, I just drew a bounding box of all BC and it just worked lightning fast. So
yeah, it will take a few seconds to load, but yeah, the other day, just I made a test, I drew a box for the whole Canada and the tool crashed. So yeah, be reasonable.
And then how do you get these layers into your local GIS if you wanted to bring this snow mask into Arc or Q?
Yeah, so you can download the outputs you generated as a georeference raster, as a GeoTIFF, and then you can add it to your GIS and overlay it with, in our case, we do it with our road layers and cut blocks.
Can you do it from your tool, or do you have to go into the code for that?
Yes, you can do it from the tool. I'm actually planning to add a kind of download button in the tool, so the user can download or export the generated output to his local drive.
And then maybe just a couple more questions, and then we'll go to the next presentation. How is the DEM acquired for this tool? So what DEM are you using?
So it's the SRTM. It's a shuttle radar topography mission, I think. It's a kind of global digital elevation model. It was acquired by NASA, I think, in the early 2000s. And it's available on the Earth Engine kind of directory. So you can add it as you add imagery or any other data.
Yeah, awesome. I think SRTM is global under 60 degrees. So
yeah, I think
once
so.
Once you go
yeah.
into the Yukon, it's not there anymore. And then last question, I like that it displays info when the satellite image was acquired. Okay, that's not a question. Okay, maybe we'll pass to the next question if there's time at the end.